Good day, everyone. In this video, let us discuss the quantum harmonic oscillator using ladder operator. We are still following the book of Griffiths, and this is Physics 141, Quantum Mechanics 1. Last meeting or last topic, we discussed the uh, infinite square wheel or the particle in a box as the first system that we studied, describing using the Schrodinger equation. So we come up with the solutions or finding or we calculated the wave functions, the stationary states, and also their corresponding energy levels. So we also provide the complete solutions, and that is by calculating the coefficient of linear expansion using the Fourier trick. Now, here comes another system, and this is all about quantum harmonic oscillator, but we will be solving the system using the approach of ladder operator. The quantum harmonic oscillator is the fundamental in quantum physics as it provides solutions to many physical problems. So any problems that involves vibratory oscillating, then the principle of harmonic oscillator is very much important, especially in quantum mechanics. For example, if the system is talking about the crystal lattice vibrations. So if we want to know the description of this crystal lattice, then we can apply the quantum harmonic oscillator. And also the behavior of atoms and molecules, since it is microscopic, but take note that they are vibrating each other because of the interaction due to the electrostatic effect of the charges, then of course it is a kind of oscillating, and of course harmonic oscillator is very much important. And many others, especially in quantum field theory. So vibratory system, harmonic oscillator is very much important. Now, if we recall the classical mechanics about vibratory problem, is for example spring. Take note that we have that unstretched length. No? So x is equal to zero means we did not compress or expand the spring. But if we apply a force, of course, we have now the displacement, which is x. We disturb the instability or uncompressed status of the spring, then of course we increase the potential energy, which is the elastic potential energy, by providing the stretch length. And of course, we apply the force. With that, if we release that, then it will undergo oscillatory motion. So it vibrates back and forth because of the potential energy and using the conservation of energy, the elastic potential energy was converted into kinetic energy, then kinetic energy to to elastic potential energy, and so on and so forth. Then, of course, we have the friction that it converts heat in the surroundings, then it will at rest. But if we consider a portion of that, we're in a certain period of time, then we can provide the harmonic oscillations. Okay? The theory says in Hooke's law that the force applied on the spring is just equal to the negative k, x, where k is the spring constant and x is the displacement, the spring displacement. Okay, so meaning we can always solve for the force, and that force can be applied in order to calculate the elastic potential energy. So meaning if we substitute the Hooke's law to the second law of Newton, then we come up ma is equal to negative kx. Of course, this is a kind of differential equation because acceleration is the second order derivative of the position with respect to time. And of course, it's negative tx. Dividing both sides by m, of course, we have that as the separable or this is kind of homogeneous differential equation. So we can solve that if we let k over m as omega, or this is the angular frequency definition, which is square root of k over k over m, then the square of omega is just equal to k over m, which means that we can replace the k over m by omega squared. So the differential equation now becomes d second order derivative of x with respect to time is equal to negative omega squared dx. So in differential equation, we can apply the auxiliary equation because this is non-repeating homogeneous differential equation. So solving for just equal to r represents the second order derivative of the position with respect to time. And we have omega for the auxiliary, no, for the non 0 degree value of x. The first degree differential is R1, but the R2 means the second order derivative. So it's taking square root of that, we come up with the solutions. So we have R, two values of non-repeating roots, I omega, positive, negative I omega. So the solution of this is kind of sinusoidal. It's oscillating. So we have the sine and the cosine. Okay, so we can actually we can the solution is exponential, no? But because we have I presence of exponent of the exponential, then we can convert that into a kind of sine function, sine cosine function. Okay, so we can please review the previous topic that we did in the particle in the box, then same process as we. So okay, so therefore we can describe the system. We can describe the oscillating body by giving its position and also velocity and so on and so forth. Now, take note that the potential energy of a spring is one half kx squared because remember, work done by spring is force times displacement, and the force is kx and the displacement is x. Okay, then extending that from 0 to position x, then we have one half kx squared. This is actually the area generated by the force position axis or graph. So if you plot the position as a function of uh, force as a function of displacement, then the graph no area by bounded by x is actually the potential energy. So that is one half kx squared. K is the spring constant, x is the compressed. So this is the potential energy for an elastic spring material. So if you graph this energy, potential energy, then we can see a kind of parabola open upward wherein we have this vertex at the origin and symmetric with respect to the axis of y-axis. So we have that graph, meaning we can always find the potential energy of the spring by giving this kind of quadratic or parabolic curve. Okay, now take note that in a problem, there's no such thing as a parabolic oscillating because oscillation is it's not always an harmonic. Okay, so what will happen if it's non-harmonic oscillating system? So let us say the potential energy is varying, depending on the x. So it's a kind of distorted, distorted. What's that? Distorted oscillating potential energy. But if we look onto its component, we can see the parabolic parts, no? So for example, we have that, no? So meaning if we have the collection of data or potential energy, we can represent it by taking portion, no? Some parts of the position potential energy that forms a kind of parabolic. So meaning we can see we have a small parabola, we have big parabola, and so on. So we can analyze Taylor system. So if we consider portion, or let's just say x naught, and that is the vertex, we can find the vertex of that collection of the potential energy, then we can use it for our system. Okay. Now, if we expand actually the potential energy with respect to x based on that graph, then we can take the Taylor series of that as the v sub naught. B prime means the first order, B double prime means second order, and so on and so forth. And we have that. Okay. Now take note that the first term is zero, no? Uh because zero, because B is zero at at x naught. So take note, we have that x naught. So at x naught, we have that expansion. So meaning the v sub as a function of x naught is just equal to zero because it is located at the origin. And the first order derivative of the potential energy, the second term, okay, is also zero because the derivative of the potential at minimum of the okay at x equal to not the derivative of the minimum is also zero. So the first term and second term can be equal to zero. The the third order derivative or higher derivative, starting second order derivative, are negligible because they are very, very small. Okay, so the significant term of the Taylor expansion is just the one half b or the second order derivative of the position, okay, or the potential energy. So in other words, we can analyze it only using the one half okay v potential energy second order derivative as a function of the position. And I take note it's square second order derivative, second order. Okay, so meaning that position potential energy as a function of position can be represented by one half v double quote or the second order derivative as a function of x naught x minus x naught square. Okay, so this potential energy describes simple harmonic oscillator. So which means that even if it is a distorted curve, but still we can find the potential energy and we can represent the simple harmonic oscillator about a certain vertex and let us say x naught. Okay, so that's why the simple harmonic oscillator is so important. The theory of simple harmonic oscillator is very important because we can again we can look into the problem that can be expressed in terms of although it's a non-harmonic, a portion of that might be a harmonic. So then we can apply the theory of harmonic, simple harmonic oscillator. Okay. Now, in quantum mechanics, what will happen? In quantum mechanics, take note that the potential energy, again, still we can use the formula 1 half kx squared, no? Where k is some constant and x is the position. Okay. And k, omega square is k over m. So you can still use that. The solving for k, then we have m omega square. And k is the spring constant. Take note of that. Okay? So which means that if we substitute the value of k, where k is m omega square, then we have potential energy as a function of position is 1 half omega m omega square x squared. Okay? So this is the potential energy for any quantum harmonic oscillator. So harmonic oscillator. Okay? So a portion of the problem in the system, we choose the harmonic oscillator. Okay, so the potential energy can be uh, calculated by using the angular frequency and also the position with the mass. It's one half m omega square the x squared. Okay, now take note that in time independent Schrodinger equation, which is negative h bar square over 2m, the second order derivative of the wave function as a function on position, plus the potential energy. So the potential energy now becomes 1 half m omega squared x squared, and we have that wave function psi, which is the position dependent only. This is time independent Schrodinger equation, and it should be equal to the energy level, okay, multiplied by the wave function. So this is now the ties in quantum harmonic oscillator. Okay, so as before, in particle in a box, we solve the wave function. No? We need to solve the wave function in order to describe the system. And respectively, for every wave function, we can calculate the responding energy. And take note, this is still in the stationary states, wherein potential energy depends on the position and independent with time. Okay, so that's why we come up with a kind of separable equation, and we derive the ties. So please refer our previous topic. So therefore, the system is stationary, still stationary states. So we have the stationary wave functions and its corresponding stationary wave energy or energy level. Okay, but the question is how to solve this kind of, because when you compare this with particle in a box, the potential energy is zero, so it's very handy, straightforward in finding the wave function. But in this case, potential energy is not equal to zero. So the question now, what will be our approach in order to solve for the wave function? Remember, the wave function is the very important quantity because it can describe the quantum system. We can provide a probability, the expectation value of the dynamical system of quantities, and so on and so forth. So we need the uh, wave function and the corresponding energy. So the question is how to solve the wave function. Okay. So there are two methods in this solving the ties for the quantum harmonic oscillator. So number one, we have the algebraic method. This is where using ladder operator, and this is our topic for today. No? Another method is we call this as analytical method, and this is using power series. That will be the next topic. Okay, so we will focus on solving the quantum harmonic oscillator using the ladder operator. Uh, quantum harmonic oscillator. And this we will be using the ladder operator technique. Okay, sige. We have the algebraic method or using the ladder operator. Now, recall that this is our ties, and this is where we want to know how much or what is the stationary state for a wave function and also the corresponding energy level. So to do it, of course, if we are using the method of ladder operator, then it is necessary to express the ties in QHO for QHO by expressing that in terms of position and momentum. So uh, we'll convert that ties into a terms that expressing position and momentum. Okay. So take note that if we transform the ties, okay, the negative h bar over 2m, second order derivative of wave function with respect to the position, it can be break into two factors. Right? Right? We can have 1 over 2m or negative h bar square, d square over dx squared. And take note that negative, okay, uh, square, okay, can be, if we use the power, no, power, if you use the power log exponent, then we can remove this square outside. Hence, this part is actually the momentum. Okay, so we can replace this for momentum. Okay, so instead of negative h bar d over dx, it is now equal to the momentum operator square times the wave function. Okay, and still we have this term. Okay, now, uh, therefore, we can factor out the 1 over 2m. So this 1 over 2m can be factored out, and hence we have this result. Okay? So this is now in terms of position, or in terms of position, which is in the presence of x, and we have this in terms of momentum. So we successfully express that in terms of momentum. Okay. Now, take note nga, this is an operator that acts on the psi. So, meaning we can call this as the Hamiltonian operator. The Hamiltonian operator now is 1 over 2m times the p squared, the moment operator squared, plus the 1 m omega x, all of them raised to 2. Okay? So, this is now the ties, okay? Ties of quantum harmonic oscillator in terms of position and momentum, wherein we know that H bar or the H hat or the Hamiltonian operator is 1 over 2m p squared plus m omega squared, omega x, quantity squared that acts on psi, and it gives us the eigenvalue energy level times the wave function. Okay, now mathematically, if we recall the binomial factor, no, binomial factor of the above, that Hamiltonian can be expressed in this mathematical similarity of if you have u squared plus v squared, we can break that into a kind of two binomials. Sum and difference of two the same binomial is actually the difference of two squares in our previous. But take note, we have the imaginary. If you multiply two i's, the result is negative I. Negative I, negative 1 times negative becomes positive. That's why we have u squared plus v squared. Okay? When we look at this, when you look at this one, okay, when you look at this one, this is quite similar to what happened here, the p square. Okay, so this is actually the algebraic method uses ladder operator. So meaning we have to use this ladder. This is now the ladder operator. We have a plus and we have a minus. Okay, so a hat means the ladder operator. Okay, so where did Griffiths find this one? This one. Okay, this is for now we use this, but later on we realize that this is actually taken from this Hamiltonian. Okay, so for now, adapt this as our ladder operator. Remember, we will solve the QHO using the ladder operators, and these are the ladder operators, the two ladder operators. We have the A plus and we have the A minus. Okay, so this is these are the ladder operators, and the goal is to express the Hamiltonian operators in terms of this operator. So this is our Hamiltonian in terms of position and momentum, but the next move is to express the Hamiltonian, which is this one, express that in terms of ladder operator. And in such, we can express the ties now in terms of the operator. And that's it. That's the strategy. And let's see what will happen next. Okay. So if we consider the ladder operator that's previously given on last slide, so we have this one, no? So of course, if you have the A plus, then you have to use the minus IP hat. That's mean. If we use the other operator A sub minus, then we have positive IP. There are two operators. Okay. So the if we use plus, we call it as the raising operator. So it's a kind of moving up, no, raising operator. While the other one is the lowering operator. So the two operators are raising and lowering operator. Okay, wherein we are given the raising operator as the 1 over square root of 2 h bar omega m omega times the negative I p hat or the moment operator plus omega x. Then, of course, we have that lowering operator. So, raising and lowering operator, we have to memorize that for now. Okay, these are very important. Anytime we will be using it. Okay. So if we try to take the product of the two, okay, the lowering operator and the raising operator, what will be the result? Okay, the question is why? Why we need to multiply this? Later on, we will use the product of the two. Okay, and we can find something. Take note, the goal is what? Our goal is to express the ties, which is position moment operator. Then we will express that ties or the Hamiltonian operator in terms of the raising and lowering operator. So to do it, the starting point is to take the product of the two. Okay, so mathematically, take the product of the two, you can distribute its term, di ba? Two binomials, product of two binomials, then the result is somewhat like that. Okay, then of course, we separate the constants in order to give emphasis. Okay, we need to give emphasis for what? We need to give emphasis for this because these are it involves operator. So the operator are the following: the position and x. X without hat, still the operator. Okay? So meaning we cannot easily multiply them algebraically. So instead, we separate that these are all constant, no? So nothing will change with respect to some parameters. But the second term, second factor are involving operators. Okay, so to do it is you have to multiply, of course, the two factors constant, then distribute, multiply by distribution. So we have that result, and we come up with this result. Distribute. Okay, and of course, the 1 over 2 each bar m omega are the result of after multiplying the two factors. Okay, some are, let's arrange, and we can notice that we have this term. Okay, so just rearranging this one and this, we have this. What is this? Take note that X and P are operators. Okay, so we have the so-called canonical commutation of relation. So since operator sila, operator, then we need to use the canonical commutation relation. So the A B, okay, which is now okay, the operator commutes B. So to, the result is we have the A times B minus E, B minus E. A times B minus E minus B. Okay. So if you look at this one from this operator, this relationship, this is quite similar to this, which means that this one is just equal to what? It is the uh, it is just equal to the commutation of X, position X and momentum. So in other words, this one is simply as the commutation of X and P. Okay, so we can replace that with this one. Okay, not not so difficult. It's just replacing that. Okay, so with that, now if you distribute the constant in such that we can form this one. Okay, so we have this kind of, we distribute, diba? By multiplication, distribute this one and this. So we have this term. So why is it that we combine these two? We have that purpose later on. So meaning we have two terms, positive and we have this negative term. Okay. Then okay, so meaning the product of the two operators, the lowering and raising operator is equal to this term. Okay. So that is our purpose. Taking the product of the two, we come up with that result. Okay. Note that uh, this commutation is a kind of operator. So if we have the commutation of X and momentum, this is a kind of operator. So operator is is a device, no, that can operate function. So meaning if we let the operator acts on something, then expect for something happens. Okay. So meaning in this case, since operator commutation is a kind of operator, then let this operator acts on any function, let us say f, then of course the expansion of this is just equal to that. Okay, then distribute the wave function, okay, or replace the momentum operator as the its definition. By definition, we have this one, and we have that. Okay, then of course we can distribute this. Okay, so or this is now equal to when we remove the negative its bar because they are constant, so nothing to worry. So we have this one, and we leave this kind of result. Okay. So then distribute this the function to the two terms, and we come up with this. This is it. Okay. Then apply the derivative. So of course the derivative of this is just equal to the derivative of the function with respect to x. While this one, take note of this, we have two factors, the position and the function. Then we can apply the product rule in differentiating. So in other words, there are three terms. So this is the first term, and this is the second term, which is now using the product rule. Okay, one at a time. Take derivative, then copy one. Then reverse. Okay, then this is the result. Okay, so we have this result. Okay, then take note that we can cancel. We can cancel this because this is exactly they're equal to each other. And we have this negative, and we have this negative becomes plus. What does it mean? That the commutation, no, of a function of the position and momentum of any function is just equal to I its bar times the same function. What does it mean? The meaning of this that the commutation of x position and momentum is just equal to I its bar. So therefore, we can replace the commutation of x position and momentum by replacing it with I its bar. So meaning this one is just equal to I its bar. Okay, so that's it. This is a kind of what uh definition of the commutation operator of the position momentum, which is I its bar. Very easy. Okay. Then replace it, of course. For simplicity, then we come up with it. So here it is. We already reflected the operator. Okay, then of course, simplify further, we come up, this is just equal to a positive one half. Okay, so so take note that when you look at the the ties in terms of position and momentum, in terms of position and momentum, this is it that we derived in our previous slide. So meaning this one, okay, without except omega, okay, and its bar, this one. So this is actually the Hamiltonian operator of the harmonic oscillator. Okay, so this is it. So meaning this is just equal to this one. The product of the two operators, the lowering and multiplied by raising operator, is 1 over its bar omega times the Hamilton operator plus 1 half. Okay, that's the reason why we multiply. Later on, we can use that. Okay, now, if we want to solve, because we are interested to what will be the Hamiltonian operator in terms of ladder operator, then solve this one and we come up with this result. Okay, so this is it. Now, previously, of course, what we did is we multiply lowering eh, by raising operator. Now, what about the product of the raising multiplied by lowering? Are they have the same? Of course not. Diba? Okay. If we follow the same step last previously, then the come up result is we have this negative. Okay. So if we reverse the order of products of the two operators, then we have this additive inverse. Okay. By the way, this is we have this, take note, we have this positive, okay? We have this positive. But if we reverse the order of multiplication of the two operators, this will become is minus. So we can obtain this by following the same steps as what we did previously. So in other words, there are two, okay? We can solve, okay? We can solve again the Hamilton operator, solving this one in terms of this operator, ladder operator, then we have this. Okay, we have two values of Hamiltonian operator. We have two values for the Hamiltonian operator. We have two values. So in other words, this is the Hamiltonian in terms of ladder operator. So if we if we have positive raising times lowering, then we have plus one. If we have lowering times raising, then we have negative one half. Okay? So this is it. This is now our final, or this is now the ties in terms of ladder operator. So it should be expressed in ladder operator. So we have that. So take note that this is Hamiltonian. Okay? Then then replace that with this one. So therefore, this is it. This is the time-independent Schrodinger equation of harmonic oscillator in terms of the ladder operator. Okay? So this is where we will solve what is psi. Okay? So how will we solve psi? Let's start with, by the way, the commutation of, since ladder operator are operators, then we have also the commutation. So the question is, what is the commutation of the lowering and raising operator? The commutation of lowering and raising operator. Then, of course, we can apply the canonical commutation relation. Okay, so the product of the two minus the reverse product of the two. Then, of course, take note that we already solved this one, the product of the two. Then we can replace the values of these two terms of the commutation. So replace that. We have this result. Okay. This is for this one, while this one we have that. So considering this result previously. Okay, then we have that result. And we can remove something, di ba? We can remove the H bar negative, this one and this one. Tama ba? Okay. So and we have that one half. So it is just equal to one, which means that the commutation, okay, the commutation of lowering and raising operator is just equal to 1. Okay, so the theorem, we have this theorem coming from Griffith's statement that if we have this psi, okay, if this wave function satisfies the equation with energy level, okay, so take note that if we let, okay, if we let the Hamiltonian acts on psi, there is a corresponding energy multiplied by the same psi. So if psi satisfies a relation with E, that is, this is it. Then, if we let the operator, okay, if we let the operator acts on psi, okay, if we let the raising operator act on psi, and that satisfies a Schrodinger equation, of course, operators here, then it will provide energy but added by its bar omega. Okay, this is a kind of theorem that Griffiths introduced. So in other words, remember that the lowering operator acts on psi is a kind of operator. Okay, which means that if we let that okay, if we let the Hamiltonian operator acts on the raising operator that acts on psi, it will come up with this one, the A plus omega, h bar omega times the operator, raising operator acts on psi. Okay, that's it. So there's something happens when we let the operator acts on psi, and it comes up with h bar omega added from the energy level of the Hamiltonian that previously known. So okay. So the question is this correct? Or what is the proof of this? So let's derive. Let's have provide the proof. Okay. So the our diba, we want to know what will happen if we let the Hamiltonian acts on the lowering operator that acts on psi. Okay. Will it provide this one? Okay, that's the question that we need to answer. So how true is the Hamiltonian acts on the raising operator acting on psi provides E plus h bar omega multiplied by the raising operator acts on psi. So is this true or false? So to do it is, of course, we need this one, this result that previously derived last slide. So substituting the values of this from the operator, remember that we have this result, okay, for the product of the two. Okay, we have already this one. Okay, so this is our Hamiltonian vector that we previously. Okay, so this one is negative h bar or h bar omega times the product of the raising and lowering and added by one half. So this is we derive this last or previous line, and this is our return. Okay, so that's it. Then continue. Then distribute. Okay, distribute the we can we can move this operator. Okay, inside will absorb this inside. So if you absorb this to this factor, then this is it. No? We have to follow the order. So since this is the left side, right side, then it should be consistently placed in the right side. So this is it, the proper way to do it. We cannot move this. We cannot move this because this is take note. This is an operator. No? We have to follow the order. So be careful for the operator, just like Victor. No, Victor sum, and we have the Victor difference, and we have also the product of Victors, wherein we have two products, the scale and that product, or that product, the cross product. Then you cannot equate the dot product and the cross product. So since this is operator, we have the order of manipulation. So we have to follow properly. So that's it. No? Okay, then next is this is an operator. So we can place this outside. We have the freedom to, but take note, this is it, no? So we have this result. Meaning we lit this to the raising, lowering raising operator plus one half, okay, acts on sine first. Then after that, we will act this raising on the result after the, okay. So that's the idea. Okay. So take note that we have these three operators. Okay. If we have three operators, meaning this lowering acts on raising, but this raising again acts on the lowering raising operator. So mathematically, we can place this outside, then wait for the result, and here it is. We let this act on side. Okay, but take note that again, there's the commutation relation of raising, lowering, and raising operator. We provided this previously, and this is just equal to 1, which means that this one, the lowering and raising operator, can be expressed, no, in terms of this expression. So meaning I can move this to the right, becomes plus, and I have this result. And here it is. I can replace this value expressing this one. So meaning if I switch the order of lowering to lowering times the raising, okay? If we switch that, then it will becomes or that value is equal to x plus 1. Okay? So meaning this one, this will becomes raising, lowering raising, it is now equal to raising lowering plus 1. Okay? So replace it. So this is it, plus 1. Then we can combine this 1 plus 1 and becomes uh okay. We have this one. Okay. Then we have okay, 1 half plus 1 half. Now in this case, what happened is, okay, so we distribute, okay, we distribute the H bar omega here, okay, we distribute here, but we move this in the next term, but there mathematics, there's no such difference on that. So if we have this raising times lowering plus one half. It is just equal to changing the order. Okay, and this is one, take note, and distribute the its bar omega. So there's no violation, no, in mathematics in this part. Nothing difference in the previous. So, but why is it that we do this? Okay, the interest is this is our Hamiltonian operator that we previously derived, which is this is which is this one. Okay, so meaning I can change that to what? So therefore I have this one. Okay, so uh, this is an operator. So meaning I can operate that here for the its bar wave function. So therefore, since why is it that we can change that order? Why? Because the Hamiltonian operator has the corresponding, this one is equal to E. So meaning this is constant, okay? So therefore I can now skip this. Okay, these are constant, so I can move this here and we have this result. Okay? So this one is very much equal to this. So in other words, what does it mean? That if we have the wave function satisfies the equation with energy A, then if we let the racing operator acts on psi, okay, then it follows that we should be added the energy, okay, which is the energy that previously known after saan na siya? After letting the Hamilton operator acts on side, then we have this one. Now, if we let the racing operator first act on side, then the result Hamilton operator acts on this, then we just add its bar omega to the previous. So that's the most important part. Okay. So therefore, this is it. No. Now, okay. Also true if because previously we say that the A racing acts on psi, okay, and I will let this Hamiltonian acts on that, and it will come up with what? Energy plus its bar omega, okay, omega of the same, di ba? Operators acts on psi, okay? Then what will happen if we have this lowering instead of raising operator? Then the difference is this will becomes minus. So we can say that if we apply the raising operator, it will level up its energy. The energy increases by how much? Its bar omega. If we let the raising operator or lowering operator acts on psi, then it will deduct the amount of negative its bar. Okay? So what's the proof of that? So the proof is okay is previous not previous method of process, the same process. So that's it. Then of course, same process what we did previously. So this one will move this. Okay, we have that, and we have this one. Okay, so that's it. Then of course we have this. We place a negative one. By the way, this is this is the E or the lowering operator from this one and this one also. But take note that this one can be placed outside first. And we let this act first. Minus one half act to this side. Side. Okay, so same process. So again, we have this one. Then we can replace that by solving this. And we have this minus one. Okay, so we have minus one plus one half. Okay, so again, we have this minus. Okay, then distribute again. Then we have this result. Okay, so in other word, by the way, this one, again, same process. We place this in the third term and we have this one. So that's why we have this again result. Okay. So this is our Hamiltonian operator. So we see that this is a negative value. Okay. So again, if we apply, what does it mean? If we apply raising operator to the side, it levels up its energy. If we let the lowering operator act on psi, it will subtract the energy by negative h bar omega. So that's why we call this as ladder operator. Okay, so it's a kind of machine, no, for generating new solutions. So if we have, for example, if we have the wave function known, no, let us say any wave function known, if we allow the racing operator that acts on that identified psi, then it level ups by how much? By its bar, diba? Omega. If we have the lowering operator, then the energy becomes low by how much? Its bar omega. So that's why we call this as the, this is just one solution, okay? One solution to get, just find one solution, then get the other. So if you have that psi is known, okay, then let the operator act on that, then we can find new one in the racing in the next level. But if we apply the lowering operator, then we can find energy or wave function, okay, with the lowest level, a low level of. Okay, so that's why we call this as ladder operator. So it's a step, no? So Griffiths provide this diagram showing the cat, no, that climbs up the ladder. So this is it. If you know this one, okay, if you know this side, if you let the up racing operator acts on this, meaning you are thinking of the next level. So one rung more. Okay. So it follows that if you do it mathematically, remember we have the lowering operator, racing operator, equivalent. Then acts on side, then we have this result E plus its bar omega. Then if we let again, okay, act again, that's why we have this secant square. So twice you do it in the second time, then of course it added another rung. That's why we have this two H bar omega added to the energy level. So that is by the use of the raising operator. Okay, then lowering operator, if we apply the lowering operator is 1a minus acts on psi, then we can notice that step down, yeah, from this rung will step down and so on and so forth downward. Okay, so the idea is if we have something, okay, if you know a one of that wave function, then you can apply the raising or lowering operator. If you are interested in the lowering low level of energy or low level of wave function, then let that act on that. Then you can solve for the energy or the wave function simultaneously. This is the idea of ladder. So that's why the harmonic oscillator, okay, quantum harmonic oscillator system, uh, we solve that using ladder operator. And that's it. We use the ladder operator. So you have to memorize the raising and lowering operator. Then that's it. Okay. So okay, let's now derive. What if we have now the ladder operator, the idea of having that? So how will we derive the the ground state wave function? So that's the first. No? Just like what we did in particular in a box. What is the ground state wave function and the ground state energy? So we are very much interested in the ground state. Take note that the ground state will actually majority of that, no, will dictates the system. So you look at the problems that we solved previously, the probability of the lowest the ground state is actually close to or almost 90%, diba? 90 or 80% more. So meaning the rest are actually coming from the other. So there is a big probability, if we know the ground state. So that's why if but if you know the ground state, then you can find the next level. So ground state is very much important. So how can we derive? How will we derive the ground state of the harmonic oscillator? Okay. So we can use the lowering operator. No? If we apply the lowering operator, or take note that the ground state occupies the lowest rung. Okay. So when we say lowest rung, the bottom. Now take note that if it is the lowest, look at it in the lowest, there's no other ladder, lowest. So it's the last in the bottom. So there's no other rung below the lowest. That's the idea. Okay, so meaning if we apply, if we let the lowering operator take note lowering, so it will step down. If we let the lowering operator acts on the lowest rung of wave function, of course, we can see nothing below, di ba? In the lowest rung. So it should be equal to 0. So that will be the starting point in order to derive this one. So we want to know what is this. Okay, so again, if we have the ground state wave function and we let the lowering operator acts on that, and remember that the ground state is the lowest rung, then of course, if you do it mathematically, you will arrive 0 because you can see nothing below. So this is the trick or the idea of providing the ground state. Okay. So making use of that, take note that we know the lowering operator. Then of course apply that. You can apply that. Okay. Up, where is it? Okay. Apply it. This lowering operator acts on psi and the answer is 0. Then we can now solve for something. Okay. And take note that P is, don't forget the momentum operator as negative its bar ddx, then substitute it here. So nothing to worry with the position operator because this is just equal to 1 value operator. It's variable, but no operations needed. So therefore, just focus on this. Okay. Then, of course, we'll distribute. No. So we can remove the negative I, then becomes negative, negative, then we have positive I. So meaning we have this positive value. So we have this result. Okay. Then of course, if you divide both sides, no, if you this is constant, no, if you divide this one, it's still 0. So meaning we can remove this. Okay, if you divide that number here, becomes 0. Okay, so we have this result. Okay, so we have this result now. Okay. Then take note our target is what is this? Then we are very easy. No? This is a kind of differential equation, a separable. Okay, so separate variables. Of course, this one should be combined here, and this dx should be replaced with here. So we have that, including the constant. So we have this kind of homogeneous or separable. Oh, by the way, x should be put it here, and this one should be. So therefore, this is it. Okay. Then what next? Of course, our dA differential equation integrate both sides, and the integral of the differential. Okay, with the speak divided by this variable, then this is natural logarithm. Okay, whereas this one is a simple integral, so we have this become squared. Okay, this is it over 2. So this is natural log. We are interested in this, so meaning convert this into what? Into exponential. So take note, this is log base a, diba? So we have log base a for the natural log. Then this one, the exponent of the Euler number is just equal to this one. So this is it, no? And we have this as a function of x. Okay, now take note we have this constant, but we can break this. Loop exponent says that it can be separate two factors, but this is still constant, di ba? This is constant, which means that we have this. This is the ground state of the quantum harmonic, or the ground state for the quantum harmonic oscillator. Okay, so that's it. Next, of course, what is C? C is constant. So in order in order to what's that? To give the normalized, okay, normalized ground state, we need to solve for C. Of course, you can use the normalization process. Okay, so normalize, of course, ensure that to be 100% to become normalized, and extend that from negative infinite to positive infinite, and take the absolute square because this is the probability density. Okay, then with some boundary limits, then the the probability of how the particle is 100%. One means 100%. So then evaluate integrals, of course. Okay, then replace. So we okay, that's it. Since we don't have imaginaries here, so just square them when we come up with this. Okay, take note C square, or this is the absolute value of square, meaning the conjugate of C times C, but still it is C squared. So you can just say it C squared. Then, okay, you have to execute take note, this is square. So this is a kind of Gaussian integral. So Gaussian integral, and okay, just remove the 2, cancel by 2, then you have to apply. So this is very important, no? In order to lessen your time in integration, then you are uh, actually allowed to use some table of constants, or of integrations. So then apply that. Of course, based on this, this is I think it will fit into this one. Meaning when, because we don't have the x here, so if we let be equal to 0, no? So n is equal to 0. This one. Okay, sorry, discard. Ay, so okay. Anyway, okay. So nothing to worry. So I think we will be using this one, and we let n is equal to 0. Okay, such that we don't have this term. So meaning we can apply. So this is it, and we need to find what is a of that. So simple manipulations in mathematics. So transform this. We have that. Our target is what is a. So give your time, no, in studying about the mathematical manipulations in such that you can form this kind of. And of course, this is it. This is our purpose. This is our A, no? This is our A. This is A. This one. Okay? So this is our A. That's it. So A is equal to that value. And N is equal to 0. Why 0? Because if we substitute 0 here, x0 is 1. So meaning we don't have x here. Tama. This one is for odd, no? For odd exponents. Or if we involve value x. Okay, so then substitute that here, then n factorial over 2, then a is this one, then raised to 2. N is 0, so meaning this one is just equal to 0, so raised to 2. And this is it, no? This is it. Of course, we have now the value of c, and c is the fourth root of this m omega over pi bar squared. That's it. So we have now the normalized, okay, the normalized value of the ground state. So this is our answer. This is very important. Take note that this is one of the stationary state, no, and it is the ground state. Okay, and it should be in the lowest rung. So we are able to derive this. Why? Because of the idea of the ladder operator. We let the lower. So the trick is there. In order to derive the ground state is we let the lowering operator acts on the lowest rung, which is the ground state. So it should be 0 then. do something about that. And that's it. We arrived at one. Okay. Now, what about the ground state energy? So the ground state energy can be calculated, of course, because we already, di ba? We already know that. So if we have this, okay, this is now the from previous. Then of course we will now, di ba? The Hamilton operator in terms of ladder is this, okay? Then of course distribute, okay, with value. Okay. If we have this as the ground state, respectively, we have that ground state energy. So the operator acts on that. Also. Then of course, this is zero. Why is it zero? Why is it that this is zero? Why is it that this one is equal to zero? Okay, analyze carefully. Take note that look at this one. We have these two operators that the two operators simultaneously act. But take note that the order of action is this lowering operator should act first, di ba? Should act to the ground state. Then the result, the next operator, which is the raising operator, acts on the whatever result here. Remember that if you let this act on that still function, di ba? It will provide a function. So meaning we can still act the raising operator. But take note that lowering operator acts on the ground state, which is the lowest rung. This is zero. There's no rung, yeah, below the lowest rung. So that's why you are the raising operator acts on zero. That's why this is zero. So we leave up with this term only. Okay? In that idea, we can solve for the energy level. Okay? Because we can remove this. And this is it. We have this one. So meaning I can easily remove that. And I can say that the energy on the ground state is one half mega. Okay. So the lowest energy and the lowest wave function was being derived because of the ladder operator. Okay. So what will be the next excited state if we have the if we have the if we have the ground state, okay? If we have the ground state, what will be the next state? First excited state and first or second energy level. Okay? So to do it is just use this one. Okay? Di ba? We have already the ground state. We have already the ground state. Okay. Now, if we have the ground state, which is the lowest rung, then we let this racing operator that acts on that rung. The answer is, of course, the result is a wave function in the next rung. So that's why, as I said a while ago, that if we know one wave function, then we can climb up and we can climb down anytime you wish. But remember, we started with ground state, meaning the only that we can do is to apply the racing operator. Now the lowering operator was used to solve for the lowest rung, but the racing operator is a factor to solve for the next level. And take note, what is AN? AN is the normalizing multiplicative constant to normalize. So meaning we need to find this one. Okay? So or you can use it because we already know this one. So you can plug in automatically the the ground state and put it here. So that's why this is the stationary states for the quantum harmonic oscillator. Take note, stationary state. Okay? Potential energy does not depend on time. So therefore, psi n means the what? The energy, the level, uh, quantum numbers. So for every quantum numbers, there is a corresponding state. No? So we have. So in this case, the why not? No. So meaning in the quantum harmonics oscillator, we can use n is equal to zero. No, we start with zero. In particular box, n starts with one, but the quantum harmonic oscillator. the quantum harmonic oscillator starts from zero. Okay? So therefore, in that case, if we have this one, if we want to know what is psi naught, okay, then what is psi naught or the ground state coming from here, then just equate n is equal to zero. So if this is zero, of course this will becomes one. So we come up with this result. Okay? And C, and of course this will become zero. So we don't have this. Okay? So therefore we go back to the, but if we wish to move in a higher rank, then n is equal to 1. Okay? N is equal to 1, n is equal to 2, and so on and so forth. Okay? So, and for the energy level also, energy level, we have this, formula. So, n corresponds for the quantum numbers. Of course, again, start from zero, unlike particular box, because in the particular box, there's no n is equal to zero. And these are all positive again. So that's it, no? That's the idea of having that one. Okay, so I think that's we will continue this. No? We will continue this because we have a lot. The big challenge there is how can we solve for n, especially if we have n greater than one, for example, or two, three, and so on. So what is so of course we will normalize. No? We will normalize. So the more number of in that you applied, okay, or enter in this one, the more difficulty occurs. Okay. So the question is, what is the technique of finding what a over n, which is the normalizing factor. Okay. But before we end, I think we have to. By the way, this is now the levels, no, just like what. Okay. I think I will show you on how to okay how to apply this before we end. We still have time. Okay. How to use this and calculate this one. Okay. Or the next level. So again, this is the lowest energy, the first excited state energy, the second excited state. So when we say first excited state, it is A1, second A2. Unlike particular box that the first excited state is A2. Okay? Because in one is the ground state. Okay? Because we don't have zero. But in this case, okay, A1, first excited state. A2, second excited. A naught, A0 means ground state. Okay, so let's find the quantum harmonic oscillator. So to find the, okay, let's us have this one. To find the state of quantum harmonic oscillator, for example, this one, okay, start with the ground state. Okay. Then of course, what next? You have to let the raising operator acts on, but the lower operator can't do it because it is already the lowest term. So of course we use this one. So that's why we use that. So in terms of quantum numbers, so this one or you can use it. So then then of course we will be using this operator for that. Then take note now we have this differential derivative. No? This one is okay, but this one is not okay. So you have to do there's a lot of work that can be done here depending on the number of bits. So anyway, it's a mathematical process. So if we start with the ground state, for example, okay, ground state, then we have this n is equal to zero. Then n is equal to one, the first excited state, and so on. So we already introduced that, and so on. Okay. So sige, before okay, let's have this example. It's coming from actually the book Griffiths, no, 2.4. The question is find the first excited state of the harmonic oscillator. Okay, so first excited state. We know already the ground state. Okay, so we have this formula. So establish. So when we say first excited state, n is equal to one. Okay, so n is equal to one. So substitute that here. That's it. So it becomes one. Okay, a n or a plus. and this will become A and becomes A1, which means this is now this is the what this is the uh multiplicative constant in order to become 100%, no? So normalize. Then of course this is okay. So that's it. Then after that, what will happen? Substitute the operator, the racing operator, substitute here. Then we come up with that. So look at this one. So mathematically, be careful on manipulations. Okay. So take note of the order. This will act. Well, this one act. Then of course we have this result. Okay. First is we introduce this one as the momentum operator. Then after that, of course, we remove the constants. We combine all constant in order not to complicate. So these are all constants, and we have here operations. This is x, so not a constant. This is exponent. Okay, so that's why be careful in your mathematics. So make sure that you don't have any violation of that. And after that, we are now ready to evaluate this and also this one. Okay, nothing to worry because there's no operation needed. But here we have this because we have the derivative. Okay, so we come up with this, and this result shows. Okay, mathematically just follow the one. Then of course, combine. Okay, then we come up with this result. That's why this twice because this is exactly the same. Okay. Then we have this. Of course, we have this x value because of this. Then this is it. This is our first excited state. Pero we need to normalize first. Okay? The first excited state, wave function. So normalizing, of course, the ritual continues. So normalize, use this formula. So we have a lot of activities in normalization. So you just go over. And be careful of your mathematics. Again, this is very critical, no? Because it involves, but take note, kine is constant, so we can move it. And also with this one, remove all the constant from the integral sign, and this is it. Okay, we have this one. Where is my pin? Okay, these are all constant, so we separate it completely. And of course, we need to do something. Again, we need the Gaussian. Okay, we need the Gaussian integrals to help us. And take note this time we have here. So it's good to use this one. Okay. It's good to use that. Okay. Then, of course, in order to come up with x squared, so n should be equal to 1. Okay. N is equal to 1. 2 times 1 becomes 2. So therefore, we have this x squared. Okay. So this is it. So transform that. So our objective is what is a. So in this case, this is our a. Di ba? Okay. So then I make this rapid. So, okay. So this is now our A, which is the transform equivalent sa ato integrand. Then apply this formula, this one, and we have this sup, supplying in, which is equal to 1, and A is equal to this one. That's it. Then we can easily find the integral of that. Okay. That's it. So therefore, we have this course, simplify. Then we can solve for A. Okay? We have to solve for A. And A is just equal to 1. So that's it. Very consistent, no? So this is just equal to 1, and we have that. Okay? So this is actually our first excited state. Okay. So the question is, what is the second excited state? It is where when we have n is equal to 2. So there, the difficulty in solving increases, no? But still, if you are consistent with the mathematics, then that's it. Okay. So we will continue this topic by what is just the again, as I've said, the most difficult part is to normalize. Okay. So what is an equal to? Then later on we realize that it can be simple, no? Because we will use the pattern on how to find this. So I will reveal this next weekend. Okay. So that's all. Thank you for this meeting. See you on my next video.